Okay, so okay, suppose a bird is flying horizontally 40 feet above your head at 20 feet per second, it's flying away from you. How fast is the angle of elevation changing when your horizontal distance from the bird is 30 feet? Your screen's still pretty. Sorry. Um, guys, on the test, I will draw the picture for you. Okay. Okay. The bird is flying horizontally 40 feet above your head. So you know that this distance is always going to remain what? 40. So that's nice. We know there's a constant in this problem here. How fast angle of elevation changing when your horizontal distance is 30 feet? Now, if the bird is flying away, we know this distance is it going to stay 30? It's going to change, right? So that's something that is important to be able to do. I'll draw the triangle for you, but you have to decide what's happening to the side that's and to the angle measures, right? If you can imagine that value changing over time, you want to represent that with a variable. But if you can imagine that length of the triangle staying the same, then you can put a number, a constant value in place of that. And so you really have to kind of just imagine this problem in motion and convince yourself, is it changing? If not, put a number there. If it is changing, I need a variable to begin the problem. Okay, how fast is the angle of elevation changing? So we're looking for d theta dt. That's our that's our goal. Let's see, what information do we have here? Well, based off of this, we can build our trig equation. So which trig equation do we want to target here? Tangent, right? So there are some problems where you can pick any of them because you have more than enough information. But this one, we're kind of restricted, right? Where we have to use tangent because we have theta, we have 40, we have information about the x, but nothing about the hypotenuse. So we're kind of forced into that tangent relationship here. Okay, we know we have to find the derivative. The left side is ready to go. The right side, though, we can avoid quotient rule because we don't have variables above and below. We can rely on power rule, but if we want to rely on power rule, what should we do? Is there a way that we can get that right side ready? Yeah, x to negative 1. Okay. Okay, we're ready for our derivative. Tangent becomes secant squared theta dt. 40x to negative 1 becomes negative 40, x to the negative 2, and what? dx dt. Let me do some cleanup here. I'll bring the x squared back down. Okay, let's go back to the problem and see what information we have here. A bird is flying horizontally 40 feet above your head. We have that at 20 feet per second. What is that referring to? Well, the bird is flying in this direction, right? So that's going to change this length, right? So this bird is flying out. It's the same as this x changing. So dx dt. Positive or negative? Yeah, flying away from us. or from the observer. So we expect that distance to be increasing. Okay. When the horizontal distance is 30 feet. 30 is what? Right, moment in time though, right? We know this is not a constant, but it is just a moment in time that's going to help us with our second triangle that we're going to build. Okay, so we have a perfect replacement for x, which is 30. We got the x dt. We're looking for d theta dt, so it should remain unknown. So the only thing left for us to find that we need is what? Secant squared, right? Make sure that you're not stuck trying to figure out what theta is. We're not going to be able to know what theta is, but rather we're going to figure out what the entire ratio is. Okay, so we go to our triangle. Let me just create a second triangle so I can just focus on the numeric values at this moment in time. 40, 30. So this is pretty straightforward here. Pythagorean theorem can get me to the hypotenuse, but we can also recognize this as a 3, 4, 5 triangle. So my hypotenuse is just what? 50. Okay. Secant of theta. What's the ratio for secant? Yeah, it's the reciprocal of cosine, right? Cosine is adjacent over hypotenuse. So therefore secant is hypotenuse over adjacent. So 50 over 30, which I can reduce to be 5/3. Okay, so we have everything that we need. We just have to plug this in and try to solve for d theta dt, right? All right, so I just have to move that 5/3 over. I'm going to square my 5/3 and I'm going to flip it over to the other side. So we can try to cancel out you're going to be without a calculator. So you can stop here and say radians per second, and I'll be okay with that. But that's the reduced answer. Okay, this form is also acceptable on the AP exam. Okay. Okay, so really the only thing new with these types of trig functions is taking that additional step of finding the ratio from this triangle, right? So right, any questions with that? Okay, number 2, find the derivative for xe to the sine of 2y plus 4x equals natural log of y. All right, so let's see if we can make some observations here. What's involved here if we want to find the derivative? We see kind of y is kind of scattered throughout this problem, right? We know there's going to be implicit. Okay, what else? Product rule, right? Okay. We also have some derivatives that we have to make sure we remember, right? E to the u and natural log of u. Here are some reminders. Okay. What's natural log of u's derivative? U prime over u, right? So these are two important ones. You're going to see those on the test, and they're guaranteed to show up on the AP exam as well. So those are one of the, I would say, one of the major ones that we're going to have to see, that we'll see over and over again. Okay, so let's go ahead and start building our derivative here. Product rule, f and g. Okay, so x becomes 1, g stays. Back to f. Okay, g prime is e to the u times u prime. When we reach u prime, we got to do sine's derivative. Okay, sine of 2y becomes what? Cosine 2y times u prime. What's the root of 2y? Get 2 dy dx. There's a lot of stuff going on here. Okay, so again, let me recap here. This is a lot going on. So e to the u becomes e to the u times u prime. U prime is the derivative of sine of 2y. Sine of 2y becomes cosine of 2y times u prime. U prime is the derivative of this parentheses, and this parentheses becomes 2, but we're asking for y's derivative, so we also need that dy dx. Okay, are we okay with that? That's the really messy part. Okay, 4x becomes 4. Okay, natural log of y becomes 1 over y. Good, right? So we're asking for y's derivative, so dy dx. Another thing just to kind of keep in mind, I think this could be helpful, is especially if you're looking at your problem and saying, wait, did I catch all the dy dx's? Did I have too many? Do I have not enough? If you look at how many y's you have to begin with in the problem, that's how many dy dx's should pop up in your derivative. Okay, so I have 2 y's here, so I should have 2 dy dx's, and I do have that. So however many y's you start off with, that's however many dy dx's you should end up with. All right, so we really have 4 terms here. So this is all connected. All this is connected. And then you got the 4 and you got the 1 dy dx. So you got these 4 terms. We want to rearrange them in a way where we can group the dy dx together so we can factor it out and divide over. So we know these are the 2 terms. This is really long and messy, but this is really just one term here. These 2 will put together. These 2 will put together on the same side, that we can factor dy dx out. And okay. So I'm going to move these 2 terms together here. So this one and this one on the same side. Going to rearrange it. I like my coefficient in front. Okay, I have my dy dx terms on the left side. I can factor that dy dx out. as messy as it is, we can just divide this over and it'll be good. I think I made some mistakes on the key here, so I think I left out that cosine 2y, so should be there. All right, any questions with 2? All right, let's try number 3. Find equation of tangent line. At the order pair. Okay, so number 3. This given domain, we'll worry about that later. We deal with our cosine, we can see how that plays a role. But right now, we can just focus our attention on finding the derivative, getting the slope, and then point slope form. Okay. So defines, well, we have the order pair, so that's nice. We know that's part of our tangent line equation. To find the slope, we need to find the derivative. To find the derivative, what's involved here? Product rule, yeah. So definitely, I mean, there's obviously a need for power rule and arc cosine, but there's also that x arc cosine together. You got to go through product rule there. Okay. Okay, f prime, x becomes 1. Arc cosine stays. Back to f. Okay, g prime is arc cosine's derivative. Remember, arc cosine is a variation of one of the 3 original ones, right? So arc cosine is the negative version of arc sine. So maybe at the end of class, we'll spend time reviewing all the rules that I want you guys to be able to do. So arc sine is u prime over square root of 1 minus u squared. So arc cosine is going to be negative u prime over square root of 1 square root of 1 minus u squared. I'll put that rule up here so we can have access to it. Okay. So negative u prime, my u value is x squared. So negative u prime is what? One minus u squared. So 1 minus x to the 4th. Okay, let me just do a little bit of cleanup and then we can start inserting our x value in and try to get this down to a number, and that number will be our slope. Okay, so there's my cleaned up derivative. Any questions so far? Okay. All right, so let's find the slope. There's no y values here, so we just plug in the x to find the slope, f prime of 0. So this is where we have to do some inverse calculation here. It's asking for arc cosine of 0. So in other words, where is cosine equal to 0? When theta is what? Pi over 2. Now, we would normally say pi over 2 and 3 pi over 2, but the way that we know that we don't go past pi over 2 is because of that domain. So that domain kind of helps us know what's value to choose for this portion of pi over 2. So f prime of 0 is going to be just pi over 2, which is the result of this arc cosine of 0 squared, minus, this is 0 over square root of 1. That's the same thing as just 0. So it's just pi over 2. Any questions finding that slope? You guys okay? Okay, so now it's easy. We have our order pair, we have our slope. What's slope form? Okay, let's yeah. So number 4, I want to rewrite number 4. It's a little bit confusing the way it's written. There's an easier way to write that problem. So let me rewrite number 4, and we'll approach 4 from this adapted equation. Okay, so let me write this out here. So instead of this right here, here's our equation. Let's make it x plus y equals more straightforward this way. Really, I'm just taking the tangent of both sides and getting that arctangent to go away. Okay, so there's our equation. Yeah. Yeah, so I'll give you one that's more straightforward if it's messy like this. Yeah, I'll give you this one right here. Yeah, your arc trig problem will be more like this, where yeah, this feels a little messy with a implicit going on inside arctan. Yeah, it won't be as messy as that. Okay, so let's do this one instead. Okay, so tangent equation means I have to get to my derivative. To get to my derivative, well, to get to my slope, I need to get to my derivative. Okay, so what's involved here? Implicit, right? We got to deal with implicit. We have y's kind of scattered throughout my equation here. Okay, so also we have to rely on tangent's derivative, right? So here's our reminder. Tangent of u is secant squared u times u prime. Okay, so x plus y, x becomes 1, y becomes d by dx. Okay, so tangent of u becomes secant squared of u. Times u prime. U prime is the derivative of everything inside the parentheses. Okay, so one term at a time, y squared becomes 2y, what? dy dx. And how about the pi over 4? Goes away, right? That's a constant, right? It's not 1/4. Pi is not a variable. Pi over 4 is a number. That number goes away, just 0. So there's two ways you can move. You can go about doing this. All we care about is the slope. So we can start inserting 1 and 0 into the derivative equation and just try to solve for dy dx. Or we can try to get dy dx by itself first and then plug in 1, 0. It's up to you. Maybe we're more used to just getting that dy dx by itself. But the advantage of plugging the order pair in earlier is it just means you can get rid of variables faster and values can combine a little faster as well. So I prefer to plug in, but I also don't want to mess with someone who's used to a pattern that we've already established. So I'll just go ahead and move things around, get that dy dx by itself, and then plug in. But okay, so there's 3 terms here. I got that dy dx, I got that 1, and I got this whole thing that's connected. This is all one term. I'll move this over to the left side. If I ever have a dy dx by itself and I have to deal with factoring, I like to put a 1 dy dx so that when I factor dy dx, I don't forget about the fact that there's still a 1 left over. It's not going to just completely disappear. I still need 2 terms, even though I factor a dy dx out. Okay, so I'm ready to plug in my order pair to find my slope. Okay, so secant of pi over 4 is reciprocal of cosine. Normally you would say 2 root 2 over 2. You flip that, becomes 2 over root 2 squared. But all this is kind of like a moot point because all this is going to go to what? It's going to 0, right? So this whole term just goes away. So I'm just left with 1 over 1, which is just 1. That's my slope. -1. Sorry. Yep. I got to bring back that -1 into my problem here. Okay. Number 5, we'll do a curve sketch problem. Page 6. Okay, so we jump directly into our derivative first. Sine 2x becomes 2x times 2. Z equal to 0. Actually, let me just call this f prime again. Okay, we're going to set this equal to 0 to find our critical points. Okay, divide by 2. Left with cosine 2x equals 0. We're not going to play. We don't want to deal with any identities here. We just used our inverse trig to help us get to our solutions here. Okay, so where's cosine equal to 0? Pi over 2. We're going to keep going, even though it looks like we're going past our interval, because we gotta shrink all those values, right? So pi over 2, 3 pi over 2. I'm going to keep adding 2 pi just so I can be safe here. I'll add 2 pi to get more coterminal angles, or 4 pi over 2. Okay, divide by 2. Same thing as multiplying by 1/2. Okay, so it looks like we have more than enough, but we know that we didn't miss anything. So we only want what's between 0 and pi, so just pi over 4 and 3 pi over 4. We create our slope sine line. Choose values in each subinterval. Again, the graph is going to be nice and alternating. Okay. Test this against my derivative function. I'll start off with pi over 6. Pi over 6 goes in for x, but it's not really pi over 6. This really turns into what? 2 pi over 6, which is the same thing as pi over 3. Cosine of pi over 3, that's first quadrant. That's going to be positive or negative. Positive. Okay, so I know that my graph is rising. Thanks. And alternate, but let's practice. Make sure we know how to do all these values here. So cosine of pi over 2 times pi, that's, sorry, pi over 2 times 2, which is pi. Cosine of pi is -1. 5 pi over 6. It's not really 5 pi over 6. It's really 5 pi over 3. Fourth quadrant, cosine is positive. Okay, what do we expect here? Relative max, relative min. Okay. Let's move on to our second derivative function. So we're working from the first derivative level. Cosine of u becomes negative sine of u times u prime. Okay. Set equal to 0. Divide by -4. Rather not deal with identities here. I'm just going to involve inverse sine, go from there. Okay, we're looking for theta values or angle radian measures. Where's sine equal to 0? 0, or else pi, 2 pi, 3 pi, okay. Okay, we have more than enough. Divide by 2. We only care about the interval from 0 to pi, so we have duplicates at 0 and pi, so it's just really pi over 2 that we have to include in our second derivative sine line. We're testing this against our second derivative function. Okay. Something nice and easy between 0 and pi over 2. I'll choose pi over 6. Here I'll choose 5 pi over 6. Okay, so pi over 6 in for sine here. It's not really pi over 6, it's really pi over 2 pi over 6, which is pi over 3. Okay, so sine of 2 pi, sine of pi over 3, that's first quadrant, so that we know that's going to be positive times -4, which is negative. So what does that tell us? This interval is second derivative, so negative means I'll do it down. Okay, 5 pi over 6. Enter that in. This is really is 5 pi over 3. Fourth quadrant, sine is negative, so negative times negative is positive. Okay, what can we conclude? There must be a what? One inflection at pi over 2, right? Okay, okay, we're ready to sketch our graph. Right, so I want to figure out where my order pairs are at the endpoint, so I know where to start my graph, and then from there I can kind of just sketch my graph along the arrows, and then I can fill in point of inflection where it lands, where lands approximately on our graph, and then from there we can get some more information. Okay, so I'm going to gather some information so I can know where to sketch my graph. So start with the endpoints here. Everything now, my most important points are my relative max, relative min, and my point inflection. Should be able to enter those in. Okay, so sine of 0 is 0. f of pi. Insert pi into the function here. Sine of 2 pi is also 0. You know there's relative max at pi over 4 and 3 pi over 4. I'm just going to go ahead and just find those points as well. So I get sine of 2 pi over 4, which is sine of pi over 2, which is 1. This is really 6 pi over 4, which is 3 pi over 2. We know sine of 3 pi over 2 is -1. Point of inflection is easy enough. We can do pi over 2 here. So 2 times pi over 2, that's sine of pi is 0. Starts at 0, 0. Ends at pi 0. Pi over 4 is at 1. Pi over 4 is at -1. Pi over 2 is at 0. Okay. Just by following the path of the graph, I know there's a relative max at pi over 4, relative min at 3 pi over 4. So rise, fall, and rise. I like to do it in 2 graphs, just get my graph going and then fill in the concavity next. I know my initially is going to start off as concave down. So I get that concave down shape here. A pi over 2 is going to switch back to concave up. Okay. I look at my graph, I can find my absolute max, absolute min. Absolute max is at 1. Absolute max is at 1, absolute min is at -1. Okay. And then we can fill out the rest of our information just by reading our slope and concavity sign lines. Guys, over the weekend, I encourage you guys to try number 6. We will do this one in class, but I think this is a good one to do. You'll see something similar to that. So if you can get that practice in this weekend, then Monday we can do it in class, and then Tuesday we can do it again. So I think the more times you can practice through it, the more comfortable you'll feel. So I also encourage you guys to look through the test, the help session packet, because I've been working through that. Those problems are good as well. So yeah, so any additional practice you can get in this weekend, I think the more comfortable you'll feel come Monday and Tuesday. All right. So if you have time, study over the weekend. I have the help sessions up from Thursday and Friday. Those links will be up by end of today, and they're under Thursday and Friday. Okay. All right, come get your phones.
Variables on one side. Images. It's like you just what I did is I had it like this.
It's east side of the door. Okay, yeah. Okay, so you moved everything to the right side. That's fine, yeah. It should
Give you a same.
be the same answer. I mean, your signs may be a little off, but it should be the same. Like if all the signs are different than this one, it's the same answer.
Question, correlated rates. For instance, when you set up the tan equation, how do you know to leave this x as x instead of plugging in your x value from?
Yeah. So the important thing is we have to kind of look at this problem and kind of imagine what's changing and what's not changing, right? So as a bird is flying, this 40 is not changing. It's staying 40, right? Theta is changing. So we know that as bird is flying away, that theta is changing. And the bird is flying away, so this x is changing.
Okay.
So we have to rely on our original information. Anything that's changing, we got to leave as a, anything that's not changing, we can leave as a constant. So even though they give you some values that is a numeric value, we don't want to insert that too soon, especially if we know that it's a moving part.
Okay.
So then once you have your equation set, you can find the derivative, and then once you need it, then you should start plugging those values in.
Okay, got it. Thank you.